Okay, so this video is meant to introduce you to Newton's laws. There's three laws. Okay, so this video is meant to introduce you to Newton's laws. There are three laws that you are responsible for knowing, like what the kind of the definition is in terms of like justifications you could point back to. That was in Newton's first law, or that was in Newton's second law, etc. So Newton's first law is probably a law that you've heard kind of the verbiage of before. But it is also called the law of inertia. And it essentially states that an object at rest stays at rest. Ooh, it's so wobbly. And an object in motion stays in motion Now here's the key part. Unless. So wobbly. Maybe that'll help. Unless acted on by an outside force. So, like this marker will just hang out there. It's at rest, it's going to stay at rest unless there's an outside force acting on it. If there's an outside force acting on it, then it moves, okay? Same idea, like if you were to throw an object, I'll roll it, so we don't want to think about gravity. If I were to roll an object, it's going to keep rolling unless an outside force acts on it. Usually that outside force is like a wall or some barrier or friction eventually hinders it. But an example of like space where there's very, very limited molecules, so there's very, very limited friction. If you were to throw an object out in space, it would just keep on going unless an outside force acted on it. So unless it got trapped in a gravitational field of a planet or something like that, okay? So that's Newton's first law. An object at rest stays at rest, an object in motion stays in motion unless acted on by an outside force. Newton's second law is more of an equation than it is it's kind of like word definition, but essentially if I were to think about it in terms of words, it says that the acceleration an object experiences is directly proportional to the net force acting on the object and inversely proportional to the mass of an object. That's a lot of words. So, oh gosh, I'm kind of sloppy right now. So if I were to kind of take this and put it in terms of an equation, it's saying that the acceleration of an object is directly proportional to the net force. And so the net force is like the sum of all the forces acting on an object divided by the mass. So this is the formal way one would write Newton's second law. But I don't really like how it's written this way. We're going to utilize it in a little bit different way. So we're going to kind of just rearrange that. So I'm going to kind of go through the derivation of that. So traditionally, this is Newton's second law, that the acceleration an object experiences is equal to the net force acting on it, or the sum of all the forces acting on it, divided by the mass. And what I'm going to do is I'm going to rearrange it so that I say that the net force acting on the object is equal to the mass times the acceleration, okay? So I've just rearranged the equation. In terms of like what depends on what, acceleration depends on the forces that are acting on the object divided by the mass. I'm just rearranging it because it's a little easier to utilize it when it's in a linear form. So I don't want you to think that the net force depends on the mass and the acceleration. That's not the dependency in this situation, okay? And I'm going to change it a little bit in that the way I like to write it is with the subscripts, because force is a vector force. There's our vector quantity. So it's really that the sum of all the horizontal forces, and I put a dot, dot, dot here because I'm looking at like what is the sum of the forces, like numerically what is, this is like a number value of me adding or subtracting forces. So the sum of my forces, and I would fill in what that value is equal to the mass of the object times the horizontal acceleration. And then the same could be said for the vertical forces. The sum of the vertical forces is equal to dot, 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 M-A-Y. Okay? So the dot, dot, dot is there to represent that you have to actually figure out what are the forces horizontally, what are the forces vertically. And then those forces would cause horizontal accelerations or vertical accelerations. Okay? And as we go through more examples and kind of problem solving, this will become a little bit more concrete. Right now it's probably pretty abstract in terms of an equation, but this is kind of our fundamental for this chapter, is this idea, okay, for Newton's second law. And then there's Newton's third law. And Newton's third law is, again, one of those laws that you probably know by heart in terms of like the words, but maybe the meaning has kind of eluded you. But Newton's third law is this idea that for every action force, there is an equal, and I don't know what I'm going to write there, an equal and opposite reaction force. Okay. So again, one of those ones that you've probably heard in previous sciences, but maybe haven't truly understood what it means. The key to really understanding Newton's third law is the fact that action-reaction forces act on separate objects. And I'm going to give an example of this here, and then I'll do one kind of in person as well. So action-reaction forces act on different objects. Okay? So Newton's third law is really kind of looking at, you've got two objects that are interacting and they're exerting an equal and opposite force with their. Newton's second law is saying, okay, if I have forces acting on an object, what are the consequences of those forces? So I want to go through an example of kind of combining Newton's second law and Newton's third law to help us understand Newton's third law a little bit better. So let's say that I have a cannon. So I've got a cannon, you know, because we're all, where's my little, I've got a cannon and a cannonball. And at some point there's going to be this explosion, right? And what happens is that the cannon is going to exert, there's going to be a force of the cannon on the ball. And then there's going to be a force of the ball on the cannon, okay? That's Newton's third law. Okay, when there's this explosion, the cannon exerts a force on the ball, but Newton's third law says action-reaction has to be true, so the ball exerts a force back onto the cannon, okay? This is Newton's third law. Now,
it's 1:30.
Oh gosh, it's 1:30. That's her computer, it always tells the time. Now, if I look at this through the lens of Newton's second law, Newton's second law says just look at the object by itself. So if I just look at the object by itself, I'm just thinking about my cannon has this force of ball on cannon, and my ball, I'm just going to draw separately. So I'm drawing these force diagrams, these free body diagrams separately. I've got the force of the cannon on the ball. Okay? So I've got my individual force diagrams, and so now if I think about the forces on my cannon, so I'm looking at the sum of my forces on the cannon. I'm only going to look horizontally. I realize there's a weight vector and a normal force vector, and in this case there's just a weight vector, so it actually would be kind of a projectile. I'm not worrying about vertical forces. I'm only going to worry about horizontal forces. So the only horizontal force acting on my cannon is this F ball on cannon. That's it, okay? And Newton's second law says, like, this is like my dot, dot, dot here. This should be equal to the mass of my cannon times the acceleration of my cannon, okay? So this is Newton's second law applied to my cannon. If I did the same thing for my ball, Newton's second law for my ball says that the only force on the ball is right here, force of cannon on the ball. So I'm going to do cannon on ball. This is equal to the mass of my ball times the acceleration of my ball. Okay, so I've applied Newton's second law to each of these objects. Now, let's bring Newton's third law back in. Newton's third law says that the force of the ball of the cannon has to be equal to the force of the cannon on the ball. So it's saying that, like, these two forces right here, they have to be equal to each other, okay? They have to be equal but opposite in direction, okay? So equal and opposite in direction, I'm just going to say that, like, this has got to be a negative, right? So if I said, oh, I'm kind of running out of room here. I can do this, maybe. Can I erase my cannon up here? I can. I'm going to have to. Sorry, guys, I didn't plan this out very well. This is saying that the negative force of the ball on the cannon is equal to the force of the cannon on the ball. But I know this is just equal to this, right? That the mass of my cannon times the acceleration of my cannon. I know that the ball of the cannon is just equal to the MA of the cannon. And I know that the cannon on the ball is just equal to the MA of the ball. So mass of my ball, acceleration of my ball. Okay, so this is kind of just algebraically substituting. Now, let's compare. Mass of the cannon compared to the mass of the ball. Mass of the cannon is huge. It's massive. I'm going to exaggerate this. Massive. There's my cannon. My ball. I'm going to exaggerate this. The products have to be equal, though. So that means that my acceleration of my cannon is tiny and the acceleration of my ball is huge. And we see this play out. We see that the ball accelerates hugely in that direction, and we see the cannon moves back a little bit in the opposite direction. Okay? So that's kind of an example of Newton's third law where the forces are equal, but they're acting on different objects in the opposite direction, so the consequences are a little bit different. Okay? I'm going to go through one other example with you in person in talking about how Newton's third law applies to the normal force. Okay? So that is Newton's three laws briefly described to you.